In continuation to the previous course on structural properties of nodes, we will focus now on subgraph properties and whole network properties, and at the end we will infer some distribution and patterns of networks. For subgraph properties, we will treat of different parts, and we will begin by defining what are components and different ways to define these components by n-clicks, k-plex, k-core, and m-core. And further, we will develop in another part the indexes for subgraph, the nodes participation contribution to subgraphs, and the specific algebra and metrics for ego networks. So what is a component? It is a connected subgraph. A connected component is when all nodes are linked to one another through paths, directly or indirectly. So each point can reach all the other points, and there's no connection outside the subgraph. So here, for example, we have a graph with two different components. They are all linked inside, but not in between both. There's a special case of isolated nodes with no links at all, and so we can define them as single components. There's some specific definition of some subgraph as the clique, which is a maximally complete subgraph. Here you have example of complete subgraph for 3 nodes, 4 nodes, 5 nodes, or 6 nodes. The n-clique is defined as a maximum path for individuals who are connected to all other directly or indirectly with no more than n links paths. So for example, the one click needs only one path from one node to the other one, so it is a complete graph. The 2 clicks needs 2 paths for every node to all the other one, 2 paths at least. And for example, a star is a 2-click as well, because there's 2 paths from every node to the other ones. A 3-click could be like this, or it could be also a circle with 6 nodes. But of course, with more nodes, it would not be a 3-click. There's also k-plex, relaxing the requirement of all members of cliques. So we ask that every node would be linked to the other one, but k of the individual of the group. So a 1-plex is a clique because it is linked to all the other nodes, but not to itself. So all but itself. So every vertex in a k-plex subgraph of size n has a degree at least of n minus k in the subgraph. So, for example, we have here the 1-plex will be the complete graph. The 2-plex will be 4 relation because here we have 6 vertices. So the complete graph has 5 vertices, 2-plex 4 vertices, 3-plex 3 relations, 2 vertices. Of course, one can mix n-click with minimum pulse with k-plex, relaxing several links. Also, we can define different ways of components. Here, the k-core is a selection on nodes degree value. So we define the connected nodes with at least a certain degree, a certain number of linkage. So if we have a network as we have in the center, if we select all the nodes with at least 1 degree, we remove the isolated nodes, which are so removed here in 1 core. In 2 core, we will remove all the nodes with less than 2 degree, so we have only here nodes with 2 degrees, the same for 3 core, degree is equal to 3, 4 core, and so on. A very nice property is that the K core have a nested property. The 4 core is included in the 3 core, as we see here. The 3 core is included in the 2 core, and the 2 core is nested, included in the 1 core. Another way is the selection on age values. So let's have a measure on the different ages, and let's see the distribution of these values of ages. If we define a threshold of m, we will ignore the ages which have less, which are below the threshold, and then we can remove all the ages, and we obtain different components. So in this part we saw what is a complete subgraph, so all nodes that are linked each other, and different ways to define them. So the n-clicks, minimal geodesic distance between nodes, the k-plex, minimal nodes degree n minus k of connected nodes in the component, the k-core with a selection on the minimal nodes degree k of connected nodes, and m-core, the minimal h value of m.